Hello, this is Professor George Easton. In this video, I'm going to explain about the factor data type in R. The factor data type is used in R to handle categorical variables in statistical procedures like regression. These are the kinds of variables that one would typically have to code using dummy variables or indicator variables. In fact, a prerequisite for this video is that you have an understanding of dummy variables in regression. The factor data type in R makes handling these categorical variables almost automatic, so they are really convenient. However, they also tend to behave in some unexpected ways and are quite likely to seem a bit weird to you at first. But they really are critical to doing data analysis in R, and that is why I've made this video to try to explain them so that you can use them effectively and they don't seem quite as strange. Before I get into the discussion of the factor data type, I wanted to point out that this video has a home page at the website datasciencesource.com where it is embedded, and I'm showing you the link right there. On that web page, you'll find additional information about the video and also a link to the R source code and the data file used in this video. While you may have gotten to this video through YouTube, it's probably best to start the video from that home page. And I encourage you to take a look at that web page to see what information and links are there. So I'm going to begin my discussion of the factor data type in R by looking at a data set, and the data are in this file myauto.csv. And I'm going to go ahead and open that, and it will open in Excel. Now let me go ahead and make this a little bit bigger so it's easier to see. And what we have in this file is data on 392 automobiles. And what we're going to try to do is explain the fuel efficiency, which is measured in miles per gallon, by 4 explanatory variables. The horsepower, which is a numeric variable, the weight of the vehicle, also a numeric variable, and then 2 categorical variables. The number of cylinders for the vehicle, which is coded as strings in this case, and it has 3 categories. The categories are 8 cylinders, and then 6 cylinders, and then everything that's smaller than 6 cylinders, which is primarily 4-cylinder vehicles, but there are also a very small number of 3 and 5-cylinder vehicles. So as represented in this data set, cylinders is a categorical variable with 3 levels. The last variable is origin, and origin represents where the vehicle was made, and there are 3 categories for this. There's American, referring to vehicles made in North America. There are vehicles made in Europe, so European codes the vehicles made in Europe, and then Japanese codes the vehicles that are made in Japan. This last column gives the model name, but those model names are essentially unique to each of the observations, so this does not represent a usable variable. So basically what we're going to be doing is trying to explain the fuel efficiency in miles per gallon by horsepower and weight, and then 2 categorical variables, the number of cylinders and the place of origin. So I'm going to go ahead and close Excel. So I'm going to go ahead and pull up RStudio that I had minimized, and I'm going to be running R using the RStudio IDE. And the first thing I wanted to point out is that this auto data set is really a rather famous data set in that it's been used in many examples. But I wanted to give the reference for where I obtained that data set, and I obtained it from the UCI Machine Learning Repository. Here's the reference for that and also the link where I obtained the data. And I have modified the data a little bit for my purposes in this demonstration, and that's why I'm calling it myauto.csv. So the very first thing we need to do is to read the data into R, and I'm going to do that with the read table command. it takes the file name and then the separator that's used to delimit the data fields, which in this case is just a comma because it's a regular CSV file. Then the header equals true tells it that there is a row of variable names. And then this last argument here, strings as factors, is one I'm going to change in a minute. But setting it to false means that the variables that are character strings will be read in as character vectors and not converted into factors. So let me go ahead and execute this command. And then I can go over to this data window over here and double click on the AutoData dataset so we can take a look at it. So there it is. You can see that the Y variable, the MPG, is over here on the left-hand side, and then we have horsepower and weight and the cylinders and the origin and finally the model name. So it looks essentially exactly the same way that it did in the Excel spreadsheet. So the auto data has been read in as a data frame, which I can test, and you'll see that that's going to come back as true. So I'm assuming that you have a pretty good idea of what a data frame is. If you don't, you should probably take a look at a video that I have, which is sort of a prerequisite for this one, which explores the basic data types in R. So a data frame is a list, and I'm going to use the function sapply, which applies a function over a list to very quickly explore the data types that are in this data frame. So I'm going to do sapply to the auto data, and the function that I'm going to apply first is going to be typeOf, which is the function that shows data types in R. So let me go ahead and execute that command, and to run each of these lines I'm using Control-Enter. So what we can see down here is that miles per gallon is of type double, the horsepower is of type integer, the weight is also of type integer, the cylinders is of type character, and this means it's a character vector. Origin is a character vector as well, as is the model. So all of these variables have read into R the way you would probably expect them to read in. But now I'm going to go ahead and re-execute this read table command, but I'm going to change the strings as factors to true, which I should tell you is the default value for this command. So if you just leave this argument off, strings as factors completely, it's going to read in the data as those strings as factors were set to true. So I'm going to go ahead and run this command again. And then again we can go ahead and look at the auto data, and you'll see that it basically looks exactly the same. Nothing has really changed from the point of view of how this data is being displayed. But if I go back now and rerun this sapply command, what you're going to see is that things are different. The miles per gallon is the same. It's still a double vector. Horsepower is still an integer. Weight is still an integer. But now the cylinders has changed from a character vector to an integer, as has the origin. The model has also changed to an integer as well. So all three of the variables that were character vectors before have now been changed to an integer. So what's going on with that? Well, to begin to explore this, let me run another sapply command here. And this time, instead of running the typeOf function, I'm going to run the class function. So we're going to see what R thinks the class of these columns of auto data are. So let me go ahead and run that. And you'll see that the class of miles per gallon is numeric. Of horsepower and weight, the classes are integer. And now the class of the three variables that were character strings are now factors. So what these data types are is they are integer vectors with a class of factor. So what we need to do is understand exactly what that means. So I think the next thing to do is to print one of these factors out. And I think the one that I'll print out is the origin. So if I do auto data origin. I'm going to print out the vector, the origin vector. So there it is. It's run off the window here. So let me go ahead and make the window a little bit bigger. There's the beginning of that vector, and there should be 392 entries. And it looks like a bunch of strings, but down here at the very bottom it has this thing levels, and it says that the levels are American, European, and Japanese. And those are in fact the 3 levels that we knew were in this column. Now this really is a little bit weird. In the data file, the data was a column of strings. But once it was read in as an integer vector, but with a class of factor. And now when we print it, it prints not like an integer vector, but rather like a bunch of strings. And it has this additional feature here on the end where the unique values in the column are printed out. Well, we know that its type is integer, so let's see what happens if we actually coerce it to be an integer. So I'm now going to print out as integer, and then auto data, $origin, and let's see what we get. Well, this time we do in fact get a vector of integers. And if we look carefully at these integers, you're going to see that they only take on the values 1, 2, and 3. So now I'm going to print out just part of the vector, allowing it to print the way it wants to as a factor, and then coercing it to be an integer to see if we can figure out exactly what's going on. So the first thing I'm going to do is to print auto data, $origin, and let's print out the first 15 values. And so what we get with these first 15 values are the strings printed out. You can see it says American, American up to Japanese, and gives us the levels just as before. And now I'm going to coerce it to be an integer. And you'll see that it comes out 1, 1, 1, 1 all the way up into 3. And if you look at this, you can begin to figure out what's going on. What's happening here is that the vector that is actually stored is the integer index into these levels to return the label that actually corresponds to the original data item. So you'll notice that the first 14 here are all American. You'll notice that the integer here is 1, so that points to American in the levels. And then the very last one is Japanese, which is the third entry in the levels. And sure enough, there's a 3 here in the vector of integers. So now we know what a factor is. A factor is a vector of integers that give the index into another vector of levels, where those levels represent the possible levels in this categorical variable. And you can see how this is a very efficient way to store this data. Instead of storing a string for every observation in the vector, and strings take a lot of space to store, what we do is just store the unique values of the string, and then in the main part of the vector we store the integer index into those levels. So if you're in a situation where you are with most categorical variables where there are a relatively small number of categories, then this is a very efficient way to store that data if you have a very large number of observations which only fall into a small number of categories. Now, before showing you how to use factors in a regression, I want to explore some of the functions that you can use with factors. For example, you can test if something is a factor using the isFactor function. So isFactor of AutoDataOrigin comes back as true. I can also use the levels function to see the levels of a factor. And so levels of AutoData$origin come back with the levels American, European, and Japanese. I can use the asCharacter function to convert a factor into strings. So asCharacter of AutoData_origin is just going to return the variable as character strings So essentially in exactly the same format it was in the data file that we read in. So let me go ahead and store this character vector. And now I can convert a character vector into a factor by using the asFactor command. So let me go ahead and store that. Now our new variable origin fac should be identical to the origin factor that's part of the AutoData data frame. And if I test this by doing origin fact is equal to, and this is the logical equals, AutoData $origin, I'll get back trues everywhere. The function factor is the factor constructor, and it actually behaves in many ways very similar to asFactor, except it allows you to specify a variety of parameters, and I'll show you that in just a second. But if I do factor of origin char, so that's the vector of character strings, what you're going to see is that it prints out the factor as before with the levels American, European, and Japanese. So there's no difference between this factor that I just created using the factor command and the vector of character strings. There's no difference between this and the factor that I read in from the data file. But using the factor constructor function, I can do things like specify the levels. For example, I might want to reorder these factors, and you'll understand more about why this is important when we get into doing the regression. So let's suppose that I do Japanese, and then American, and then European, and go ahead and construct this factor. You'll notice that I get exactly the same vector as before, except that the levels here are reordered. So if I go ahead and slide up here, we can look at the tail end of the factor vector when I just constructed it without specifying the levels. And this last row, for example, is 3 Americans, a European, and 3 Americans. If I come down here to the factor that I created specifying the order of levels, you'll see that I haven't changed the data. I still have 3 Americans, European, and 3 Americans, but the ordering of the levels has changed. If I leave one of the levels out, so for example, I'm going to go ahead and leave out American and create this factor, what you'll see is that everywhere that there was an American before, there's now a missing value. So the factor function can be used to create factors and specify the levels and the order of the levels. Next, I want to show you what the attributes of a factor are. So if I use the attributes function on the origin variable of the AutoData, what it shows for the attributes is a list with 2 items in it, levels and class, and the levels are the levels of the factor, the same thing that would be shown by the levels function, and the class is factor, which is what would be shown by the class function. So now I'm going to show you why factors are so convenient in R. And the reason is that functions like linear regression recognize the factor and automatically take care of creating dummy variables in order to estimate the regression model. So let me go ahead back to the editor window here, and we're going to go ahead and use this AutoData to fit a regression. So I'm going to begin to run the regression by specifying the model that we want to fit, and I'm going to store that in a variable called fn. So you'll recall that we were trying to explain fuel efficiency. So let's just look at the AutoData again. We were trying to explain fuel efficiency, which is measured by miles per gallon, by the explanatory variables of horsepower, weight, the number of cylinders, which is a categorical variable, a factor, and then the continent of origin, which is also a factor. And I've already explored this data a little bit, so I know that in order to get a good linear fit, we need to look at the logarithm of the miles per gallon and also the logarithm of the horsepower and the weight. So I'll specify my model as follows. It's going to be the log of the miles per gallon, and I'm going to be explaining that by, and you use a tilde when you're defining an equation in R that's going to be used as a model specification in a fitting procedure like linear regressions. So that tilde kind of replaces the equal sign, but it indicates that what is being specified here is a model. Now, in a model specification such as this, the constant term is assumed, so you don't have to put anything into this equation to indicate the constant. And so the next thing we need to do is specify the x variables. The first x variable in our model is going to be the log of the horsepower, and then the log of the weight. And then we're going to use the categorical variable cylinders. And then finally, we're going to use the origin, which is also a categorical variable. So that's going to specify the equation for our model. Then we're going to fit the linear regression using the LM for linear model function, and I'm going to store that in out. So linear model, and then the first argument of linear model is the equation that you're trying to fit, so that's going to be Fn. And then I need to tell linear model what data frame to use to try to find these variable names. So data is equal to auto data. So this line of code will fit the linear model and store the fit into the variable named out. And then finally, I want to print out some output, so I'll do summary of out. Let me go ahead and run these 3 lines of code. So the first one again is defining the model equation and storing it in a variable called Fn. The next line is actually going to fit that model, looking for those variables in the data frame autodata. And then finally we're going to print some output. So let's take a look at what we get here. Well, here is the coefficient table that shows the estimated regression coefficients together with tests of whether or not these coefficients are 0. And so if we look down this table, the first entry is the intercept, which is generally not what we're most interested in. The next variable is the log of the horsepower. We'll see that the coefficient is negative, and the p-value here is virtually 0, which means that this is highly significant. So not surprisingly, as the horsepower goes up, the miles per gallon go down. Then we are looking at the log weight variable. The coefficient is also negative, and it's highly significant. So again, as you might expect, as the weight of the vehicle goes up, the miles per gallon goes down. Now if we look at the cylinders, we'll see that we get these 2 entries, cylinders 6-cylinder and then cylinders 8-cylinder. And what these are the regression coefficients for the dummy variables for the category 6 cylinders and 8 cylinders. And so this is taking the very first level, which was the category 3, 4, 5 cylinders, as the base case. So the linear model function has recognized that the cylinders variable was a categorical variable, and it's taken care of the coding of the dummy variables more or less automatically. You can see that the coefficient for the dummy variable 6 cylinders is negative and significant, indicating that the 6-cylinder vehicles have lower gas mileage than the 4-cylinder vehicles. And then you can see that the coefficient on the dummy variable for the 8-cylinder vehicles is also negative and bigger than the coefficient on the dummy variable for the 6-cylinder vehicles. And this is indicating that the gas mileage for the 8-cylinder vehicles is even worse in comparison to the 4-cylinder vehicles than is the gas mileage for the 6-cylinder vehicles. So these regression coefficients are behaving as we would expect. And the same thing now has happened with the categorical variable origin. Origin has been recognized as a factor and coded with 2 dummy variables. So we get 2 coefficients in the table here, one for origin European and another for origin Japanese. So the base case for the dummy variables is taken to be American. And we can see that the miles per gallon for the European cars, the coefficient is small and negative here and not significant. So this is suggesting that there's no difference between the American cars and the European cars. If we look at the dummy variable for Japanese cars, however, you'll see that it is positive and it is significant at the 5% level. So there's evidence here that the fuel efficiency of the Japanese cars is better. So I want to show you what's going on behind the scenes, so to speak, and you can see what's actually happening by using a function called model.matrix. So returning to the editor window, if I use the function model.matrix, and it takes as its first argument the equation that specifies the model, and then I need to tell it the data frame to use, so that's auto data. And if I run this function, what it's going to compute is the actual X matrix that's used in the regression. So it was just computed and flew by on the screen, so let's go ahead and take a look. It's a matrix with 392 rows and 7 columns. Moving up to the top of the model matrix, what we'll see is that there is a column here labeled intercept that has all ones in it, which corresponds to the intercept term of the regression. The next column contains the logs of the horsepower. The third column contains the logs of the weight. The next column contains a dummy variable for 6 cylinders. So it's going to be 0 anytime the vehicle is not in the 6-cylinder category, and a 1 every time it is. What comes next is a dummy variable for the 8-cylinder category, and it's going to contain a 1 every time the vehicle is an 8-cylinder vehicle, and 0 when it's not. And then the last 2 columns are dummy variables for European origin and Japanese origin. And so these dummy variables are going to take on 1 when the vehicle originated in that category and 0 otherwise. So just to make absolutely sure, let's print out one of these dummy variables and the corresponding factor so we can really verify that the ones are in the right place. So I'm going to go back to the editor window and actually save the model matrix. And then I'm going to create a data frame that has the dummy variable for the 8-cylinder category from the model matrix as its first column. That happens to be in column 5. And then the factor from auto data for the cylinders. So first I need to rerun the model matrix command to store the model matrix and create the data frame which has printed out in the console. And so what we can see when we examine this data frame is that sure enough, any time the vehicle is an 8-cylinder vehicle, the dummy variable is set to 1, and any time it's a 6-cylinder vehicle or a 4-cylinder vehicle in the category 3, 4, 5, it's going to be set to 0. Now the last thing I need to talk about is how functions like the regression function LM know what level of a factor to take as the base case. And the answer to that is it takes the first level as the base case. So if I print out the levels of one of the factors, so auto data $cylinders say, what we'll see here is that the level 345 cylinder is the first one, and so it's the one that's going to be taken as the base case, and that's why we saw regression coefficients only for 6-cylinder and 8-cylinder. There is a function called relevel which allows you to change which level is the first one, and therefore allows you to reset what is going to be interpreted as the base case in functions like the regression function. And so I'm going to very quickly show you an example of that. I'm going to change the cylinders factor by releveling it. And the new level that I'll use as the base case will be 8 cylinders. And so if I run this line of code, I will have changed the base case for the cylinders factor. So let's just see if that's really happened. So I'm going to print out its levels, and sure enough, 8-cylinder is now the first one. Now if I rerun the regression, and print out the results, what I'm going to see is that for the cylinders factor, I now have a coefficient for the 3, 4, 5 cylinder level and for the 6 cylinder level, but no longer have one for the 8 cylinder level because the 8 cylinder level is being treated as the base case. So now you know how functions like LM determine the base case in R and can reset it if you prefer a different base case. So this concludes my discussion of factors in R. I've shown you what factors actually are. They are integer vectors together with a list of categories in an attribute called levels. And I've also shown you how they're interpreted in the right way in fitting functions such as linear regression. In such functions, dummy variables are created for those factors automatically, which is an extremely convenient feature.